Hello students. So today we are going to continue with the cubic crystal system. So I am going to share here the PPT. So in the last lecture we are up to the crystal cubic system or cubic crystal system, and we have already learned that the corner particles are shared by the 8 unit cell, and hence the unit cell, the single unit cell will have the 1/8 part of the constituent particle which are at the corner. So this 1/8 part of the constituent particle are inside the single unit cell that we have learned. Okay, in the bcc structure, body centered cubic structure, all the corners particles are shared by the 8 unit cell, means every corner particles here can be shared by the 8 unit cell, which we have already learned, and hence in bcc the 1/8 part is inside the single unit cell, and along with there is a one particle which is at the center of the body or center of the unit cell, which is not shared by any kind of unit cell, which is belonging to the entire that single unit cell. And this is a space lattice. In the fcc we have learned in the last lecture that the all the corner particles are shared by 8 unit cell. So each corner particle is shared by 8 unit cell. There are 1/8 part inside the single unit cell at each corner, so each corner is is in adjacent to 8 unit cell. Each corner is adjacent to 8 unit cell. So 1/8 part is inside the single unit cell of each corner, and plus in this there is one half part of the constituent particles are uh, remain inside the unit cell. One half part at the center of the each face is inside the single unit cell. And this is all about the space lattice of face centered, body centered, and primitive cubic unit cell. Now we are going to learn that inside the single cubic system, inside the single unit cell of a cubic unit, every cubic unit cell, how many particles are present? How many constituent particles are belonging to the cubic unit cell of all types? So let us going to learn here. So this is again cubic crystal systems. So these images are very useful to understand the exact concept of the solid state, and I am again expressing the courtesy for these images which we have taken from the internet. Now here the simple or primitive cubic unit cell. Now it is very clear here that all the corner particles is in having 1/8 part inside the unit cell. This is a perfect representation with this module of the unit cell, and hence if 1/8 if you add all 1/8 part, then the total number of particles in the unit cell becomes 1. So 1/8 multiplied by 8, because there are 8 corners, so 1/8 multiplied 8 becomes 1. So unit cell, primitive cubic unit cell, contains one particle. Overall it contains one particle. Now, in the second type here, the BCC structure, you can see here that in the BCC structure, these are the corner particles here. So 1/8 multiplied by 8, it becomes one particle. So in the BCC structure, there is one particle is present because of the corner. Contribution is from the corner is one particle, and inside the cell there is a one particle. That means total particles are present are 1/8 multiplied by 8 is equal to 1 plus 1 at the center of the body, that is called as a 1 plus 1, it becomes 2 particles present at the in the BCC crystal structure, or body centered cubic crystal structure. Now we'll go further. This last is FCC structure, face centered cubic structure. As you know that the from the corner contribution from the corner is 1/8, from each corner the contribution is 1/8 1/8, so total becomes 1. So 1/8 atoms from the 8 corners becomes one particle, and half atoms at the face, half atom at the each face, 6 faces. So 1/8 one half into 6 becomes 3 particle. So overall particle in the cubic crystal system becomes 1 plus 1 half into 6 is 3. So 1 plus 3 is 4. So this is very important that the crystal system, sorry, crystal system or unit cell contains how many particles. So again I am given this diagram from the textbook. Here you can understand that how the particles are arranged in FC, then BCC and FCC here. And this is the same as which we have learned. The model is same here. And then we go for the how many particles does each unit cell of cubic crystal system contains. So in the cubic crystal system, the number of particles are in the simple or primitive cubic, it contains 1/8 into 8 is equal to 1 particles. Then the number of particle in BCC, that body centered cubic unit cell, is 1/8 into 8 is equal to 1, and one particle at the center, it becomes total 1 plus 1 is 2. And FCC, in FCC it contains 1/8 into 8, that is 1, plus 1 half into 2, 1 half into 6, because there are 6 faces, so it becomes 3. So total number of particles in FCC is 1 plus 3 is 4. So this is very important that the primitive cubic unit cell contains one particle. The body centered cubic unit cell contains two particles, and face centered FCC means face centered cubic unit cell contains total 4 particles are present in this type of crystal system. Then we go for the next, that is called as how the particles are arranged to form a crystal lattice. How the particles are arranged to form a crystal lattice. So there is a stacking of the particles. There is a stacking of constituent particles here, and because of this stacking of constituent particles, actually we get the that type of unit cell. So stacking or packing of constituent particle is very particles are closely packed. This is called as a packing also. If they are very closely spaced in the unit cell, then the packing is very efficient, and hence we get different types of unit cell. So formation of unit cell, it depends upon how the constituent particles are arranged or how compact they are arranged. That system is also a definite system, or that is a systematic arrangement of constituent particle. So let's learn about this type of system here. Okay. Before that, I think there is a small topic. We will finish this small topic to find out the density, molar mass, and age length of the unit cell, and then we go for the packing of the constituent particles in the unit cell. Okay. Now here we are supposed to calculate the density and molar mass and how it relates with the edge length of the unit cell. You know that the density of the substance is fixed. Whether you take 1 gram of the substance or half gram of the substance, its density is fixed. So here the edge length, the edge length of the unit cell is A, and here the volume of the it becomes A cube. So why it becomes A cube? So we are talking about the edge length in terms of the for the cubic system here. So the volume is same, A and A edge length, width, and the uh, length, width, and height is same, so it becomes A raised to power 3. So here the volume is becomes A raised to 3 because A is the edge length of the unit cell. So mass of the particle is here M. Mass of the particle here is M, and N is the number of particles present in the unit cell. So mass of the particle is m, the number of particles present in the unit cell are n. Then we can say that mass of the unit cell becomes m into n. The mass of the unit cell becomes m into n. So why it becomes m into n? Because as a whole we can say that unit cell is having identity because of its particles. Unit cell is having identity because of the particles which are present inside the unit cell. That's why we are counting how many particles are present inside the unit cell. So unit cell as such has identity because of the particles. So mass of the unit cell is nothing but the mass of the particles present in it. Mass of the unit cell is nothing but the mass of particles present in it. So how many particles are present in it, that is called as n number, and mass of each particle is taken as a m. So we are talking here for the metal crystal actually. So density of the unit cell, next third point is density of the unit cell rho is nothing but the density of the substance. You know that density of the substance does not changes. So whether you take 1 gram, whether you take 0.5 gram, or 1 micron, or even if unit cell, its density is same as that of the substance. So the formula for the density, you have to remember only one formula for the density, and that is, I think, very useful to calculate the further calculations here. So rho is equal to mass upon volume. This is the important formula. Is rho, that is the density, is equal to, this is rho, that is density, is equal to mass upon volume. So here mass of the unit cell divided by the volume of the unit cell. So what is the mass of the unit cell? Simply the mass of the atoms or particles present in it. So m is suppose the mass of one particle, small m, then number of particles if it is n, then mass of the unit cell becomes m into n. Simply the mass of the particles becomes m into n. So this is m into n divided by A3, that is the volume of the unit cell. This becomes overall density. Now, how can you calculate this is the only formula you have to remember. Now, how you calculate the mass of a single particle? For this, there is very useful formula. You should not forget, this is very useful. And here, the Avogadro's number will help you us. Here, the molar mass of the substance M, capital M, is denoted by, for the molar mass is equal to the mass of the particle here multiplied by Avogadro's number. So Avogadro's number of particle, their mass is molar mass, nothing but molar mass, or molar mass is the mass of Avogadro's number of particle. Molar mass is nothing but the mass of Avogadro's number of particle. So if you want the mass of one particle, if you want to know the mass of one particle, that is small m, okay, so it is simply the molar mass divided by Avogadro's number. The molar mass divided by Avogadro's number. So here the last formula, that is rho is equal to n into capital M divided by Na. So simply we are substitute the value of m here, and we get this type of formula, that is rho is equal to n into capital M divided by A3 volume multiplied by Na, Avogadro's number. So this is the only formula. If you are confused in this formula, just remember this formula, the back formula here, and put the value of small m, which is m divided by Na. You get this formula. If you know this formula, from this formula, if you know the values of all, you can able to calculate the age length of the unit cell, that is A. So you are able to calculate the age length of the unit cell if you know the molar mass, density, Avogadro's number, and if you know the how many particles are present in that unit cell. So this is very amazing that you are going to calculate the age length of the unit cell, which is very small here, and then you can understand that how small is the unit cell that as compared to that of the crystal. Okay, then we go for the next. As I told you that we are supposed to know about the packing of the particles in the crystal lattice, means how the crystal lattice is formed. As I already told you that the particles are arranged here, and this arrangement or this packing will decide that what type of unit cell is formed here. Now for this you must know the coordination number. So what is coordination number? In the simple language or simple words, we can say that it is the closest neighboring number. It is the closest neighboring number, or we can say here that it is the number of neighboring spheres that touch any given sphere. The number of neighboring sphere that touch the any given sphere is called as its coordination number. Here the particles are considered as rigid sphere. Here the particles are considered as a rigid sphere. So we are onwards slides, we are supposed to call this particle as a sphere here. So this is all about the coordination number. Now here you know that the crystal structure is made up of the three dimensional um, packing or three-dimensional arrangement of the constituent particles. But so as to understand the three-dimensional arrangement of constituent particle, we must know about the one-dimensional packing and two-dimensional packing of the constituent spheres or the particle. So let us go for the first one, that is called as a close packing in one dimension. Close packing in one dimension. Why it is called as a close packing in one dimension? But I told you that here, if the packing is closed one, then the coordination number is higher. The close packing means how tightly the spheres are packed in the unit cell, or how closely they are packed in the adjacent sphere, with the adjacent sphere. So this will decide that how the coordination number is less or more. If the coordination number is higher, that means that unit cell is closely packed. If it is not closely packed, what happens? Let us see here also in the next slides. So here the close packing in one dimensions, here the this is a textbook images A, B and C. So we are using here, this is the first image A, that is called as a close packing in one dimension. The spheres are arranged in a row. Here the spheres are arranged in a row, they are touching each other. Here the coordination number is 2. So if you select any sphere, it is touching to 2 sphere only, that is the coordination number. Okay. Now close packing in two dimension, this is one dimension, first one. Second is related with the two dimension figure. So this two dimension means two is a planar structure, or in a two direction here, x and y axis, so it called as a two dimension. So in the two dimension structure, if you take the one dimensional arrangement of the sphere, and it is aligned vertically and horizontally, then it becomes the two dimensional. Then it becomes the two dimensional. Now this two dimensional packing is takes place by two ways. This two dimensional packing is takes place by two ways. So here first is the from the image, that is B, and second is from the image that is called as a C image. So first is close packing in the close packing, uh, square close packing. First is called as first way for the two dimension is square close packing. So in case of a square close packing, the one dimensional rows are aligned vertically and horizontally. So you concentrate on the first row in the B image. So this is the first row, and the second row, the alignment of the second row is same as that of the first row. So alignment, if it is same either vertically or the horizontally, then this kind of packing is called as a square close packing. So this way the alignment is same as that of the A. Also it is called as A type of alignment also. And here if you observe here in the images here, so you can observe that if you take select any sphere, it is in close contact with all these four sphere. If you select a sphere here also selected in the image, it is in close contact with the four sphere, hence the coordination number is 4. So any sphere in the square close packing touches four other sphere. If you if you draw the lines, if you draw the lines which are passing through the center of this four sphere, okay, or if you connect this their center of this four sphere, you get a square. You get a square. That's why it is called as a square close packing. That's why it is called as a square close packing. The coordination number is 4. Okay, so this is all about the square close packing, which is very important. Then we go for the next, that is called as a hexagonal close packing, called as a C. That is called as a second way for the two-dimensional hexagonal close packing. In hexagonal close packing, in hexagonal close packing, that is the C here, the first, there is a horizontal row. The first row is called as a type, suppose, horizontal row, and the second type is called as B, and this B row is different from that of the first row. The second row is alignment is different from that of the first row. So in the depression, you can understand here that there are depression in the first row, okay, or the free space in the first row, and the second row is fitted in the depression of the first row. That's why its alignment is different, okay, and hence it is not same as that of the first row. So if alignment is say different, then we call this layer or this row as the B row or B layer. Okay, so there is the first is A row and second is now B row. If you put the third row now, so third row alignment is same as that of the first row. Third row alignment is same as that of the first row. Third row is also in the depression of the second row. Third row is also in the depression of the second row or free space of the second row. So that's why if A, then second row is B, then again it gives you the third, that is third layer, which is again same as that of the first, that is called as A. So the pattern here is AB pattern, and hence this kind of structure is called as a close packing in two dimension, called as a hexagonal. Why it is called as hexagonal? Because if you select any sphere here, if you are select here, it is already selecting here the pair sphere here, and its close neighboring spheres are 6. The close contact neighboring sphere here are 6. So this 6 number is called as a coordination number. This 6 number in hexagonal close packing is called as a coordination number. If you join the center of all these, you get a hexagon. If you join the center of these 6 spheres, you get a hexagon. So that's why it is called as a hexagonal close packing in two dimension. So this is the description. See here, whatever I explained for this packing is same is you have to write in terms of the description. So here I am written the description which is same as what I explained, that here the staggered arrangement is result if the second row is fitted in the depression of the first row. See here the arrangement is called as a stagger, just which we have used this word for the conformation of the organic molecule staggered and eclipse for the alkanes. So we are using the term staggered arrangement is result if the second row is fitted in the depression of the first row, and here the both the rows are different, they hence they are called as a AB type of row. Now third row alignment is same as that of the first row, and hence it is called as ABA pattern, or the fourth row alignment is same as that of the second row. So the pattern here is ABAB, or we can call it as a AB type of arrangement. Coordination number is 6 here. Now very important thing is that the free space here, the free space between all these, if you see here in the close packing, the free space here is called as a voids here. The free space here is called as a void. So this is the first layer A, this is the second layer, and not only these voids, but here there is a called as a voids, and there are two types here. The apex of these voids are also the important. These voids are triangular in shape, you can notice here these are triangular in shape, and the apex of these voids are arranged in a uh, Here these apex of these triangular voids are upward direction for the first row, and they are in the pointing downwards for the second row. So this is also important, that here they are um, pointed upwards, and here apex are pointed downwards. So these are all here. You can see here that in this arrangement, close packing arrangement, the coordination number is higher. If the coordination number is higher than square close packing, then we can say that which is more compact. So hexagonal close packing is more compact, and hence the square close packing is not that much compact because the coordination number is less here. And also here the voids is the size of the voids is small. In case of square close packing, the voids are bigger, the free space is bigger in size, the shape is also bigger. Here the free space is triangular here, and size is also less. So this is all about the packing in the two dimension, and in the next lecture we will go for the close packing in three dimension. I already told you that, for so as to understand the close packing in three dimension, we must know about the close packing in one dimension and the two dimension. So let us stop here, and we will continue in the next lecture.